Hello everyone, welcome back. In this video, we're going to talk about skewness and how the data can be distributed in different ways. So we're going to talk about 4 different ways that data is commonly distributed. We'll talk about data that is distributed in a symmetric way, a uniform way, a right-skewed way, and a left-skewed way. We'll talk about how we can identify these different types of skewness by looking at visualizations of the data, but also how we can identify these different types of skewness when looking at numerical statistics of the data, like the median and the mean. So let's go ahead and start off by talking about symmetric data. And so here is a histogram of an example of a set of symmetric data. And so on our vertical axis, we just have frequency. And then on the horizontal axis, we have our data values. And we're not actually looking at any specific examples here, but this is what a typical histogram might look like. And so as the name suggests, we have this really nice symmetry when we're looking at symmetric data. So to define that a little more particularly, if we have symmetric data, then we should be able to kind of cut it perfectly in half with a vertical line. And so our data is going to be symmetric if a vertical line can cut it into 2 kind of mirror images. So one half reflected over that vertical line gives us the other half. And how might this symmetric distribution be represented in the actual numbers of our data? Well, we'll have symmetric data when the mean and the median are the same. So the mean and the median should be the same when we have symmetric data. That is not necessarily true of the mode, but oftentimes it will be. Right, to see why the mode doesn't have to be in agreement with the mean and the median, just look at our histogram here and imagine these 2 sidebars were higher than the middle bar, then the mean or the average would still be right in the middle, but the mode would be larger and smaller, of course. But then we'd see that the mean and the mode are not necessarily the same. So next we want to quickly talk about uniform data, or data that is distributed in a uniform fashion. And this is just really a special case of symmetric data, right? We still have that vertical line that is roughly cutting it perfectly in half, creating 2 mirror images. And the mean and the median are going to be the same when we have uniform data. It's just shows up often enough that we kind of give it its own special name. And so uniform distributions show up all the time in statistics. A really easy example to wrap our heads around is imagine you're rolling a 6-sided dice and you're rolling it a bunch of times and your values are 1 through 6 and the frequency of how many times those numbers have showed up. Well, each one has the same odds of being rolled, so we expect that distribution to be uniform in shape if we were to actually roll it and record the values that we rolled. And before I forget, another couple phrases that you'll hear pretty often when symmetric data is being discussed is like normal curves or bell-shaped curves. And this first example of a symmetric data is also an example of a normal-shaped curve or a bell-shaped curve, right? If we were to kind of sketch a continuous curve over our histogram, it gives us that classic bell shape that you'll see all the time in distributions in statistics. So just as a heads up, if something is being referred to as a normal or a bell-shaped curve, this is the kind of image you want to have in mind. It's an example of symmetrically distributed data. All right, so up next, we want to talk about right and left skewed data. And to me, I always feel like these names should almost be mixed up. But let's go ahead and clarify why we call these right and left skewed sets of data. And so when we visualize the data in these histograms, it looks like we have a big clump of data to the left for right-skewed data and a big clump of data to the right for left-skewed data. And to me, that's almost a little counterintuitive, but that's not what we're trying to capture when we say something is right-skewed or left-skewed. What we're really talking about is the mean or the average. Just intuitively looking at a set of right-skewed data like we have right here, the center is in this large cluster of data. I think that's where our intuition thinks the center should be. However, if we actually evaluate the mean or the average, we find it's actually a little bit to the right of this large clump because of these kind of extreme values out here further to the right, or these smaller values. So because the average is pulled further to the right than we might visually think it should be, that is why we call it a right-skewed set of data. All right, so for right-skewed data, the mean or the average is going to be pulled further to the right than we might intuitively think it should be, and that means that the mean is going to be greater than the median. Remember, the median is where half the data values are below or above that, and that will be in that kind of large cluster of data that we see there, but the average or the mean is going to be slightly to the right of that. So when the mean or the average is bigger than the median, that's an indicator that we're looking at a right-skewed data set. Another thing that we can do is kind of draw a continuous curve over our histogram like we did for the symmetric data, or that normal curve over here. And when we do something like that for right-skewed data, it might look something like this. And what we see is that we have like a nice thin tail off to the right side of that curve. And that's another way to identify that right skew data. Does the visualization of our data in something like a frequency histogram have a nice little tail on the right side? All right, and the last type of skewness we're going to look at is going to be that left skewed set of data, and that's really just the reflection of our right skewed data. All these same kind of points are true, but reversed or flipped over. So instead of our mean being pulled to the right like it was for the right skewed data, now these kind of smaller values over here outside this large cluster are going to pull our mean or average to the left instead. And of course, just like before, the consequence of the mean or the average being pulled away from the median is that, well, now the mean or the average is going to be to the left or smaller than the median. And our left skew data is also going to have a tail to it, but this time the tail will be on the left side. And so if we try to draw that nice continuous curve over the top of our data, it'll look something like that. And here we have our thinner tail on the left side of our data, another way to identify that left skewed set of data. All right, now that we've talked about these 4 different types of way our data can be skewed, we also want to talk about what is the best measure of the center for these different types of distributions. When we have symmetric data, like our first 2 examples, it doesn't really matter because things like the mean and the median are going to be the same anyways. So it doesn't matter if we use the mean or the median as the measure of center when we have symmetric data. However, if we have right skewed or left skewed data, then the mean or the average is not necessarily the best center anymore. As we mentioned briefly in our earlier discussion, when we have right or left skewed data, the mean is going to be pulled to the right or to the left and be over-influenced by some of these smaller or larger values in the data set. And so because those values are having more influence than we think they should, we don't think the mean or the average is the best measure of center when our data is skewed left or right. Instead, we are going to use the median or the interquartile range, IQR, as the measure of the center instead. That'll give us a better measure of the center and kind of match up more with what we kind of visually see as like, well, these large clusters are where the center of the data should be.